Great. So I'll try not to overrun this morning. I mean, there's a huge amount to talk about. I'll try and squeeze it into focusing on deep geothermal power development and what we've done at United Downs and where we currently sit with United Downs. So for those of you that don't know me, I'm Ryan Law. I set up geothermal engineering back in 2008, 2009, specifically to look at geothermal power in the UK and to try and prove that it was possible to develop geothermal power successfully and to prove that the whole industry really could be developed from this. So geothermal engineering now has a number of spin-offs and we continue to push forward in different areas. So what we'll focus on today is United Downs. United Downs is actually a limited company. It's a special purpose vehicle which has focused entirely on the United Downs project near Truro in Cornwall. We also have Geon Energy, which looks at geothermal heat only, and that's doing some quite interesting work. It's a joint venture with Arup, the consulting engineers, and we're currently doing some interesting work on actually very topical conversion of oil and gas wells to geothermal heat. So that's one area we see that's really growing both in the UK and other countries. And another entity called GeoCube, which is looking at direct lithium extraction from deep geothermal fluids, another very, very hot topic right now and very, very interesting when it comes to the resource in Cornwall. So that's sort of how we've split and continue to expand into different areas of interest. United Downs project per se was designed to prove that geothermal power is possible in the UK. And finally, it will be online and producing power at the end of 2022. It's been a very, very long story, which we'll cover in hopefully in this brief time this morning. It's pretty much now a 30 million project. It's funded by a mixture of ERDF, which is European Regional Development Fund. Cornwall Council, Cornwall is very, very proactive on deep geothermal and other renewable energy sources. So I think they've shown what can be done when a local authority really gets behind something and can start to shift and create and make things happen in a way that perhaps couldn't be done without their level of support. And we also have private investors in the project, a mixture of equity funding and debt funding as the project develops. And the key thing is, it is this demonstrator that the UK can indeed produce power and heat from its geothermal resources. It's been a long story. We started this concept back in 2009 when I launched the company. We then pretty quickly moved through site location and site acquisition. It's an area that all of us, particularly on the development side, do need to think about. It's quite hard to find sites that tick all of the boxes. So, I'm often asked the question, how big is the geothermal resource, whether it's heat, whether it's power in the UK? And actually, that's not really the question. The resource is substantial. The question is, how many sites can you actually find where you could theoretically run a deep drilling operation onshore and connect to the grid and potentially have heat offtake nearby and ensure that you can get a rig to the site and all the associated infrastructure that comes with that. So it's not as simple as just saying, yes, the geothermal resource can provide whatever it is, 7 gigawatts of power. Maybe, but it is tricky to find sites that suit, and that's not just true with geothermal. It's true with any other renewable source that has to develop onshore in the UK or within Europe. Any onshore development is difficult to get through all the permits, processes, and community acceptance to make these things happen. So we moved through site acquisition and permitting and achieved the first planning permission for a geothermal power project. So I had to really think about how that works in practice. And then it took about 5 years to get the funding together. That was very difficult. Probably not surprisingly enough, when you're proposing to drill deepest wells in the UK, not easy to convince at the time private investors that any degree of risk mitigation was possible. So that did take a long time to get over the line. We ended up with this mixture of public and private. I think today's climate is different, both metaphorically and in the real world, and it's become easier perhaps to fund these sorts of projects, but back then it was very difficult. So once we actually finally got the funding in, we then shifted through procurement, drilling, and we completed these very deep wells in 2019, the deepest of which is 5.275 kilometers beneath the site. They're both directional wells. And then we spent a long time, partly COVID related, but also we needed to do a lot of testing and development to really understand how this deep reservoir works and how we could develop it. And, you know, we're now at the point where life has started to become relatively easier, where we move into sort of conventional contracts with construction of the power plant and PPA, in this case with Ecotricity, if they manage to survive. Depends how many electricity suppliers go down over the next 12 months. So we're in relatively a good place now, having been through a long period of difficulty and really interesting aspects of deep geothermal development. I think everybody knows why we're doing it in Cornwall. I won't dwell too much on this slide. Cornwall does have a very high heat flow. It all comes from the granite rocks. The granite is effectively a massive nuclear power station. And what we've done is really try and tap into that heat producing granite, with the key aspect of granite, as most geologists know, does not really have much permeability. So water does not move easily through granite, particularly at 5 kilometers. Therefore, we've targeted these very, very large fault zones that exist within the granite in Cornwall, which we assumed would both have water content and enable water to move through the rock, the sorts of flow rates we might need for commercial production. So that was the key thing about this project: target the fault, see what happens when you drill through it, and hopefully the fault will operate in a way that enables you to sustain geothermal power production. So this is shown conceptually on the left here. We have a deep production well, a 5.275 kilometer well, and we have a shallower injection well. They are both within this substantial fault structure. The fault structure is pretty much vertical, and one of the things about the project was it's quite easy to see these faults at the surface. Obviously, they are substantial and pretty much 500 meters wide. But the real question is, you know, did they extend to the sort of depths that we wanted to target? Because if some of our calculations were out, we wouldn't hit the fault. We'd intercept it at a too shallow level, in which case it'd be too cold. So it was quite, I wouldn't say difficult. It was almost it was almost like having putting a lot of money on a certain number on a roulette wheel, because you really didn't know what was going to happen when you're down at this sort of 5 kilometer level. You know, you think the fault's going to be there. Is it going to be in the right place? And you know, I am a geologist, but I understand that it is you know, it's an art as well as a science. And our chief geologist did actually pretty much get the location of the fault right. It was there. We were within sort of 10, 15 meters of where we predicted it would be. And you suddenly saw differences in the way the drilling rig was behaving, the way the drill bit was behaving, and you're starting to lose fluid. So that was one of the key things to prove, was the fault was there, and it would at least have some degree of natural permeability. So we drilled and completed both wells, and And obviously the resource was hot enough, yeah, relatively easy to predict what the temperature might be. We were at the end of the well, we were about 187 degrees centigrade. And one of the other aspects of the project, which really is important when you're talking about these deeper projects, is the alignment of the background stress regime. Now, as a geologist, we didn't really cover much of stress. That's more in geomechanics world. But those of you that are involved in geothermal will know there was a big hot dry rock project, research project in Cornwall before we did this. And one of the key findings of that project was that the background stress regime enabled water was shown to move vertically downwards. So in our case, when water is injected under pressure. So in our case, we had this combination of a vertical fault structure and a background stress regime that would enable water to percolate downwards between the two wells. Well, that was the theory anyway. So there's a couple of pictures of a nice big drilling rig. Everybody likes a big drilling rig. This one was about 55 meters high. Very impressive piece of kit. And these are the two wellheads in our nice clean site, pretty much how it stands at the moment. And the aim was always to produce up to about 3 megawatts of power, more than likely through what's called a binary power plant. I really like this slide now. It kind of summarizes exactly what you need from a geothermal project, particularly a geothermal power project in these deeper resources. So temperature, there's only really two things you need to make a project work, even though it takes a long time to make it happen. There's temperature and flow rate. Now, those are your main controlling factors. So we kind of knew we were in the right target zone for temperature because temperature is relatively easy to predict. We had no idea whether we'd be in the right zone for flow rate. We were targeting sort of between 15 and 60 liters per second of water flow. And then this slide in the middle is something that becomes very, very important, which is the pressures required to both pump that water to the surface from the deep well and to inject the water back into the rock. So there's this point at which you want those pressures to be as low as possible, yeah, and for both economic drivers and also for reducing the risk of induced seismicity. So there is this key aspect that for these deep systems, how much pumping power do you need to pump the water to the surface? How much pumping power do you need to inject the water back into the rock? And what is your risk of induced seismicity? The lower all of those pressures are, the better for economics and the better for reducing risk of induced seismicity. So that was this pressure aspect was something we really did work on a lot during the sort of longer period of 18 months of what we're calling reservoir development post the drilling of both wells. I brought this slide up on induced seismicity because it is important for these deeper projects. Down in Cornwall, we were governed by what's called surface acceleration, which really means how are things felt at the surface, yeah? And in Cornwall, there is a limit for quarry blasting in terms of surface acceleration, which is about 8.5 millimeters per second. There is a much higher zone of 15 millimeters per second, which is when you potentially might see cosmetic damage to buildings. And then way down here at 0.5 millimeters per second is what we set our caution limit at. So we really wanted to be highly conservative in how we stimulated these wells and how we controlled induced seismicity. I think I'm sure some people in the audience will know what happened to the shale gas industry post some induced seismic events that were very felt at the surface. So we were very mindful that we did not want both community to be upset and also for the geothermal industry as a whole to be stymied by induced seismicity and induced seismic events. we had a lot of fun with this. We could talk about this for a very long time. This is just one slide of this gray line is the deep well, okay, into the rock. And these tiny dots are induced seismic events. So we had a very, very precise network that could identify very, very small events at depth. And slide on the left is sort of when we started some of this reservoir stimulation. And slide on the right is kind of when we finished. You can see there are many, many more microseismic events. But more importantly, for the operation of the system, we expanded the reservoir to over 50 million cubic meters. So the reservoir at the end of all of our development, and it was a long drawn out process, and I have to say we learnt a great deal en route. It became something that was more viable for the sort of production that we needed. Had we been sort of in the middle of nowhere in the US, we probably could have pushed it a lot harder and caused many more seismic events and much larger seismic events that would probably have hugely expanded the reservoir, but undoubtedly the events would have been large enough to very much annoy the local community and potentially put the geothermal industry at risk of a bad reputation. So we were trying to manage the needs of reservoir development with community concerns. I think in the end, after a lot of learning, we probably managed to do that pretty well. This image here is where we finally got to July this year. After all that work, we tested the whole system in the sense that we produced water from the deep well and we injected water into the shallow well at the same time. And this is a really nice picture of geothermal steam from 5 kilometers down beneath the ground. At the site, this is our steam separator, and you can see a lovely steaming lagoon from where water just sub 100 degrees C is coming into the lagoon, and the rest is being flashed off in this very, very well designed steam separator unit, which is effectively a huge, large steel can. So that was a great moment where we finally got there and we realized that the system would work. And this really stems back to how difficult it can be to develop these sorts of projects, because it's really only at this point, that's a long time after we started drilling, that we knew the system was going to work. So that is a lot of capital spent at risk until you get to this point. It's why it's hard to make these things happen. One of the other big things we did was community engagement, and I have to thank Jane Charman, who works for us as our community engagement manager. She really did a great job of getting out there and speaking to as many people as possible and bringing as many people as possible on board to help them understand what it is we're doing. There is always a lot of concern with any development. There's particular concerns with very big drilling rigs coming into a site, and it's hard work to try and continue to educate people, to try and stop rumors being generated about all the strange things we might be doing on site. It's something we took very seriously from the start and continue to do so. And I can't stress enough the need to have dedicated people who are willing to go out there, be on people's doorsteps, face the music, face the anger, face the concerns. I mean, obviously, generally, most people are very, very positive about what we do, but you need to try and win over as many hearts and minds as you can with these sorts of projects, because we don't want situations like a shale gas scenario where you're literally unable to do anything on site because of community lack of acceptance. So great job done there. We continue to do a lot on that. And now we're moving on to other sites. It's again, a process that has to be started once more. So I think we learned a lot about education, how to run these things, how to present materials, and we continue to do so. But for any project developer, it's absolutely key. And the other aspect, which is really interesting, and it's one of my personal bugbears, about why you need to go out and do stuff in the real world, okay? So when we started this project, it was a really just try to aim it as a commercial power project. Where it ended up being is a huge research entity. So we had 2 big Horizon 2020 projects linked to this, linked to the United Downs, big European research funding, big budgets, a lot of science brought to the project and continues to be brought to the project. We recently have another project called OptiDrill, which is another Horizon 2020 project looking at how to refine drilling. And really, I would have had no idea that when we started this, it would have attracted so much attention. We've now moved on to direct lithium extraction trials. We do have a great deal of lithium, fortunately, in these deep geothermal wells, actually the highest concentration in the world, which is great. And that's enabled us to make a lot of progress with trialing what's becoming a really interesting industry, which is effectively zero carbon mining from deep geothermal projects. So all of this additionality came because we started it and we got on with it and we moved the project forward. I can't stress enough the need to start things, make something happen, and people will come and join you. So when we did start, we were looking at power only. Obviously, geothermal heat is a big product of these systems too. And you may have seen some of the news about the Cornish Geothermal Distillery Company that is aiming to produce geothermal rum from some of our waste heat. So fabulous that that's coming to the site too. And more research projects likely to come from what we've learned about reservoir stimulation. So, one project has kicked off all of this additionality. And we would hope, that will continue as we move on to other sites. So really trying to sum up in a few words, some of the challenges and what one should bear in mind if you're trying to do some of this stuff in whether it's Ireland, Northern Ireland or other projects. There are a lot of challenges to make these things happen. It's why you're not seeing hundreds of deep geothermal power projects starting all over the UK. The risk stroke reward, that's what I bang on about a lot, is a difficult one to sell. Yeah, it is not that strong, i.e. the risks are high, the rewards are not as high as oil and gas. So it was very difficult to fund United Downs. In fact, it was impossible to fund it on a purely commercial basis. Now, that's no longer the case for what we're doing in terms of future sites, because we have reduced the risk by proving a project. But it's very difficult in a new area, whether it's Ireland or Northern Ireland, for example. It will be very hard to 100% commercially fund a project of this nature because effectively the resource is unproven. So there will always be some need for grant support for the first projects. It was also very, very difficult for an SME, we're an SME, to run a project of this scale. Cash flow is difficult when you're running a drilling operation of this nature. Something to bear in mind for those developers trying to do something. Think about getting a deep pockets partner involved. It's hard for an SME to do this. It'd be easier for us on the future sites because we'll have a much greater sort of funding base to draw on, but not easy as an SME. As I mentioned, the capital is at risk for a long period of time. We started drilling 2019. We only really proved the reservoir in this summer, 2021. And so the capital has been tied up, really pretty much for at least 4 years, and you still don't know whether it's going to work. It takes a committed investor to back that. And further to this, some of the grant funding mechanisms are not necessarily suited to a project that can very quickly change budgets, because drilling is expensive. Drilling can suddenly require another 10 days of drilling. Before you know it, you need another £1 million. And those decisions have to be made very quickly. And grant funding mechanisms are not fast in terms of changing how they approach a project and how they fund a project. So there's a lot of things to think about as a small company and how you might fund this. On the technical side, we mentioned the fault identification. Difficult to identify these deep faults through any meaningful method of geophysics without drilling them. So that's a tough risk. There's also quite a technical risk when you drill through these fault structures at depth. We had quite a few issues with drill bits. There can be issues with drilling with mud losses. They're a little bit unexpected. And reservoir stimulation, we talked briefly about induced seismicity and how that might impact operations. We've seen this in other projects within Europe recently where very unexpected levels of seismicity occurred, despite even the best forms of modeling beforehand. So you really have to be super careful about that and do expect, as I've said, the unexpected when you are stimulating some of these deep wells. And every project will be very different with different problems, whether it's community, whether it's logistics, whether it's stimulation and other problems that might come with that. I don't think any project will ever be the same. So where are we now? Having been through this sometimes painful process, but very positive process over the last year, we're now heading off to 4 other sites to do exactly the same thing. Slightly bigger, aiming for 5 megawatts net per site for power, and also a great deal of heat off the back of that. We have now submitted all of the planning applications for those 4 sites, and we hope that by the end of the year, we'll aim to have those permits in place so we can get on and do this. And one of the interesting things that we are thinking about for these next sites is also this potential for mineral extraction. I feel we've really only just started to look at this for a potential geothermal revenue stream that helps immensely in how you might fund some of these projects. Power alone, it's quite difficult to make the project stack up. If you can add some heat and you can add some potential minerals, then the projects start to look pretty attractive. And we aim to develop those a lot faster than we've done at United Downs. As I've said, we lost about 5 years at United Downs raising the funding. So this should be a lot faster in today's political and economical climate. These are where the 4 sites will be. And I really just wanted to add this slide because if you're looking at Ireland or you're looking at Northern Ireland or any sites within the UK, there is no perfect geothermal site. You need this combination of geology that works, but also logistics. Do you have grid connections? How close are the local population? Is there fresh water? All these things that come in to a site, particularly community acceptance. What are hotspots? Will you get permission in certain areas or not? It's difficult. We filtered through something like 27 sites, potential sites, in terms of good geology, and really shrunk it down very quickly to what would be actually possible in the real world. So it does take quite a lot of additional work beyond geology to find sites that you can successfully develop on. And that is where we will wrap up today. That's about 12 years of my life summarized in about 30 minutes. So hopefully that was of use. And now we're open to any questions.